Hello, my name is Mike, and today we're building a nonlinear circuits Bindubba sequencer from a kit. This kit took about 7 hours to build. As always, this video is not sponsored. I bought this kit with my own money, and the background music to this video was made using the Bindubba sequencer. First, we're sorting out the components. We're going to start with the ICs, then the transistors, then we will alternate between the resistors, capacitors, and diodes. After we have all the surface mount components done, then we'll move on to the power connector and the front panel hardware. Because the surface mount components are so small, each value of the resistors and capacitors come in their own little baggies. Here I'm plotting out which ICs I'm going to tackle first. In general, I want to start in the middle and work my way outward. But there's areas on the board with a lot of space and areas on the board that are more crowded. Each IC has a line on one side. We need to make sure that line is on the same side as the notch printed on the PCB. When soldering surface mount IC chips, we first want to add solder to one of the corner pads. Then we position the IC with a pair of tweezers and then use our soldering iron to melt the solder that we already laid down. We then want to carefully hold the IC in place, then move the soldering iron away, but we keep holding the IC in place for a few extra seconds so that the solder becomes solid again before we pull the tweezers away. You will see me release too early several times throughout this video. We use a generous amount of flux on every connection because flux helps solder flow across the metal components and the metal PCB pads. One way to think of it is that the flux helps draw the solder towards and also helps spread it evenly across the metal. If we see a solder bridge, we want to use flux with our soldering iron to help pull the solder towards the metal parts and away from the gaps between the legs. It also helps to flatten down and spread out excess solder. Here I make a couple of mistakes. On the second from the top, I wanted to add solder to the corner pad, but I missed and hit the second one instead. This isn't a huge deal. But on the next one, I accidentally solder a second corner pad on the same IC because I thought I was soldering a corner pad for the next IC. The IC shifts as I'm applying flux, indicating that the solder connection wasn't strong enough. I use a copper braid to suck up some of the solder I added to the second corner pad. I'm trying to drag excess solder on one leg over to another leg that needs more. Now we're done with the ICs, so we're moving on to the transistors. These transistors are tiny and challenging to work with. We must take care not to use too much solder with connection points this small. Here I'm showing off how tiny these transistors are and how tiny their 3 legs are. The strategy with these is to add solder to one of the pads, hold the transistor in place, melt the solder on the pad, then go back and add solder to the other 2 legs. Here I squeeze the tweezers too tight and the transistor goes flying. Even in super slow motion, we can't see it flying off to the side there. I had noticed that the front panel diagrams were on the same side as the SMD components, so I was wondering if somehow the Minijacks and Potentiometers were supposed to be on this side of the PCB. I took a break and confirmed that the front panel hardware does indeed go on the other side of the board, based on photos on the Nonlinear Circuits website. With the transistors done, now I move on to the other SMD components, resistors, capacitors, and diodes. I notice that there are markings on the board that say 104, and I think those refer to the 0.1 UF capacitors, but I'll need to confirm that later on during my next break. Some stray solder flies into a hole for one of the potentiometers. I try to fix it with my soldering iron, but that doesn't work, so I need to use the copper braid. I also got some solder in this tiny hole called a via next to this resistor. I try to work it out, but then I take a break and look up a diagram and decide it can be left alone. I have since learned that toothpicks come in handy for getting stray solder out of vias, so in the future I may try that instead. This is after I've confirmed that the via connects to the adjacent resistor, so I decide that I should hit the resistor with a little bit of solder again to make up for all the solder I removed trying to open up this via. Sure enough, the solder flows straight from the resistor to the via, so I'm pretty sure that's just how that is. Once again, I get solder in a through hole, but this time I'm able to clear it with a copper wick on my first try. Now I have solder in one of the LED through holes. I've never had so much trouble with getting unintended solder into so many through holes before. This is the point when I confirm that the 0.1 UF capacitors do indeed go on the PCB where the markings say 104. The 0.47 UF capacitors are marked on the PCB as 470N. These are the same value expressed different ways, in microfarads and in nanofarads. Now we're doing the diodes. These diodes are like little orange glass tubes with a black stripe on one end. That black stripe must be on the same side as the line with an arrow pointing to it on the PCB. With the diodes in this corner of the board completed, now I want to fill out the rest of this area with the remaining resistors. Now my strategy is to finish off the rest of the 100K resistors and the 104 capacitors before moving on to complete the left side of the board. There are resistors labeled on the PCB as RL. These are resistors for the LEDs, and their values can vary depending on the types of LEDs used. In this kit, 16 of the 4.7K resistors pair with the 16 LEDs, so those resistors go where it's labeled RL. The remaining 4.7K resistors go where the board is marked 4K7. The 1K resistors that are in line with the RL resistors. I almost missed a lone diode way over here on the opposite side from the rest of the diodes. I was hoping I'd have a spare one for another project I have coming up, but unfortunately no. doing the rectifiers. You can see there's a dot on the right of each one printed on the PCB. The line printed on each rectifier must be on the same side as that dot. And with that, we're done with the surface mount components and we just have through-hole components left. First, I add the power pin headers. Next are the Vactrols. Instead of positive and negative markings, the PCB has the letter A and the letter K. The instructions on the Nonlinear Circuits website do not remark on this, so I had to resort to Google. The A is for anode, and the K is for cathode, even though cathode is spelled with a C. The cathode in this case is negative. Now, the cathode isn't always negative. In the case of a battery, the cathode is positive, but here it's negative, I think. I am fortunate to have built kits with Vactrols previously, so I already know the longest legs go on the opposite side away from the positive and negative markings, and that the leg marked with a dot is negative. If I had never encountered Vactrols before, this could have really thrown me for a loop. Now we're placing, but not soldering, the Minijacks. I've never had a PCB with such large holes for the Minijacks, and as a consequence, they are seated really loosely on this board. Next, we have to prep 18 potentiometers. First, we have to remove all the nuts and washers from every potentiometer, and then we have to snip off this tiny little nub on each one, otherwise our faceplate won't sit flat. Luckily, I happen to have an old pair of end cutting pliers that are perfect for this. I've decided I should probably place the LEDs before placing the potentiometers, but I'm having trouble telling which way to orient the LEDs. The long leg on each LED is positive, and the short leg is negative. On the other side of the PCB, there's a diagram where one side of the LED is flat, which corresponds with negative, but if I already have the Minijacks loosely placed, and I want to double check which side on the PCB is negative, I have to lift up the board and look underneath. Predictably, a bunch of Minijacks fall out. So now that I have the LEDs placed, I decide to do the potentiometers before redoing the Minijacks. The potentiometers at least fit snugly in their holes and aren't likely to fall out. Now that all of the front panel hardware is in place, I fit the faceplate over the potentiometers and Minijacks and screw on the nuts to the 4 corner components. I want to solder the LEDs in place first so I can snip their legs and get those out of the way. It is very important to make sure the LEDs are properly sitting in their holes on the faceplate before soldering them, and I like to check a second time before I solder the second leg of each one. Now I'm screwing the nuts on the rest of the front panel hardware to hold it in place and ensure each component is at its proper height before soldering them. Next, it's time to solder in the Minijacks and Potentiometers. It feels like the large holes for the Minijacks are too big, but I don't want to worry about any more of the Minijacks falling out now that the faceplate is in place, so I solder the smallest pin on each Minijack first. My first thought when soldering the large holes for the Minijacks is that I must have done something wrong. This feels like it takes too much solder. I worry that there's large glops of solder on the other side of the board, but I check and everything looks fine. At some point, I confirm that what I'm doing is correct, and this is how the photos on the Nonlinear Circuits website look. Now we solder the 3 small pins on each potentiometer, but we're going to leave the larger location lugs until last, just in case we need to rework anything. In this build, it may not be necessary since we seem to have free access to pretty much every component on the back here. Now I do a quick continuity test on the power pins just to make sure there are no shorts. And here is the Bindubba sequencer. First things first, we do a power test to make sure there are no puffs of smoke or anything ominous like that. Here we see that there are 2 lights on at step 14 and step 16, indicating already that something is wrong. I enter a clock signal in the horizontal input and see that step 14 is always on. When I put a clock signal in the vertical input, step 14 turns off, so I hope everything's okay, but then when it gets back to the bottom row, step 14 is once again always on. So it looks like we've got some troubleshooting to do. The first thing I do is look for anything obvious, and then I kind of zero in on the immediate area of the potentiometer and LED of step 14. I consult the schematic, and I'm not good at reading schematics, but it seems like the LEDs connect to the CD4081 IC chips, so I look at those and I think I see a completely unsoldered pin on the one in the last row that corresponds with step 14. That might be the problem. I also reflow all the other pins on that chip just to be thorough, as well as the LED for step 14. And I think I might also see a bridge between the pins for the potentiometer on step 14. So with all of these things corrected, hopefully one of them is the thing. So we try testing the module again. Alright, test number 2. We don't have number 14 on, so that's good. Let's go ahead and hook up some clock signals. And voila, step 14 doesn't stay on. Don't worry that it's not going exactly in order. That's a feature of the Bindubba sequencer. The vertical and horizontal clocks are independent, so in this case, it's moving down on the 4th step of each row. That's fine, it's working as intended. I continue testing and everything appears to be good. Now that we have a working module, the next step is to solder those location lugs on the potentiometers. Finally, we want to place and secure the knobs. These knobs have a tiny little screw that needs to be tightened to hold them in place. Even my smallest screwdriver isn't small enough for these screws, so I have to resort to angling in the corner of the flathead to tighten them. And here we are, the Bindubba sequencer. Thank you so much for watching this video. If you enjoyed it or found it useful, please consider liking and subscribing. Have a great day.